everybody, and once again, welcome on this Tuesday/Friday, before noon. We'll continue today with the lectures on fundamentals of telecommunication, and we will move on to we discuss some theoretical aspects of what is actually information and how we can measure information. So I'm just sharing the screen. And of course, routine questions, if you can see the slides and if you can hear me. If one person can speak up, please.
Yes, we can.
Brilliant. So before we move on, are there any concerns or any questions related to the content we've discussed so far? Or okay, I don't see anything, so I assume things are more or less clear. So just kind of to recapture the key components and the key ideas as we'll be continuously discussing them. So we spoke, among others, about the free space attenuation, right? So there's this idea that we have some source of a radio signal, or in general source of any electromagnetic wave that is carrying our signal in unbounded medium, right? And we know from Hoyen's principle that such a source should generate a spherical wave which propagates over space as time passes by. However, from the preservation of energy law, we also know that the total energy of such a wave need to be constant, right? So we are assuming here the lossless case. So there is no attenuation. So by lossless, we mean that there is no energy or no radio energy that is converted into the heat or converted into dissipated into other forms of energy, right? And even in that lossless case, we can see that as we move away from our source, the same energy per area that we can interact with our antenna. So over here, we are assuming that this is the area from which our antenna of the receiver gathers the signal, the electromagnetic energy. And we see that while we move away, the energy or the power that we can receive from the transmitter deteriorates with a power 2, right? So basically, again, if you want to have the same amount of power here at 3 times the distance, we actually need 9 times more power at the source, which is, of course, not very efficient, but that's just how physics works. So we cannot do anything with that. And this is basically given by this equation, right? So we have the total power radiated simply divided by the area of the surface at a distance r. So based on that, we also talk about the Wi-Fi and different modulation types. And you should know by now that basically higher modulation, by higher we mean using more symbols, can transmit information faster, right? Because you can encode more bits in a single transmitted symbol. However, they also require better signal strength, as they are more prone to error in the presence of noise. And this is also what we discussed last time. So the blue curve, again, this is the theoretical power that, or how it decays with distance in a Wi-Fi system at 2.4 gigahertz. Again, assuming a perfect condition, so no walls, no furnitures, but we'll discuss that especially later in the lecture, right? And you can see that the minimum threshold is over here, right? So at a certain point up to this distance, right, the power is sufficient to communicate over 64 QAM. Then it deteriorates, so it needs to be switched to 16 QAM, which is slower, and so on and so forth. And at certain range, it's difficult to receive any communication. And normally, this is something, of course, that is embedded into your wireless routers. So you're not even aware what the type of communication is based on the quality of signal. Your router will automatically switch between those modulations, and there are certain protocols, of course, to ensure this is synchronized. So, well, in any case, if you want to have, higher, probably intuitively observe that by yourself, right? If you want to have a faster internet, you should simply, move closer to your router. That's okay. Now, another thing which we discuss is the signal-to-noise ratio. Apologize for the mistake here. And this is, again, a cornerstone in telecommunication and many systems, right? So basically what it means that in most systems, we're actually not interested in absolute power of our signal to assess quality of the signal, but we are interested in the ratio of the useful signal power to the noise power. And this is called a signal-to-noise ratio, right? And basically it means that certain noise level allow us to distinguish between different amplitude levels. Okay, so, and this is basically what is embedded into the standard, right? So what I showed you earlier, right, with the distance, that with the in the slides before, that I told you that the distance over here requires changing of different modulation schemes, but this is actually done for the fixed noise level. Okay, so over here we assume that our noise is fixed, right? And the only thing that changes is the power of our signal as proportion to the distance, which in turn, lower power tends to mean lower signal-to-noise ratio, right? However, of course, the things in general case can be reversed. So we can have a constant signal power, but increase the noise or actually increase the interference as well. So interference can be, by interference, I mean, different radio signal that run concurrently to your own, right? So basically, this is in decibels, in logarithmic scales. And you can see here that different modulation schemes require different SNR to offer the same bit error rate, right? To offer the same amounts of acceptable amounts of errors per bit or percent amounts of bit. What I want you to pay your attention, which might be actually not very well seen here, but so in general, if we speak, for example, for the 4FSK, which stands for frequency shift keying, right? The frequency shift keying actually requires much higher, higher signal-to-noise ratio than simply the phase shift keying, right? So this is something that should be kind of taken into account here, right? And the more complex modulation you have, the more the higher your signal-to-noise ratio should be, right? So up to the so remember again, this is in decibels, and up to the very high 256 QAM modulations, which would typically require 27.8 decibels, which is quite a lot actually, if you think this is a logarithmic scale. Okay, another thing we spoke was the channel and how to quantify channel capacity. And basically, the basic Nyquist theorem is very simple. So we take double the bandwidth of our channel, and we take logarithm base 2 out of m, where m is the length of our alphabet, right? So the discrete number of signals, right? So basically, it is quite intuitive so far. So so the more symbols we have, the faster we can transmit our information, right? Because we have a bigger choice of symbols, and I will quantify a little bit more on that in the when we move to the Shannon theory and the information concept. And of course, the channel capacity increases linearly with the bandwidth B. So that's for the noiseless case quite again hopefully intuitive. And an example here is that the 3.1 kilohertz bandwidth, which is an old analog phone, which can carry binary signals. So by binary, simply logarithm 2 based of 2 of 6,200 bits per second. And that might seem like a very slow those days, but originally, actually, that was the typical speed of the first modems before the invention of ADSL. So generally speaking, in early 90s, when the internet originated, there were no people would typically dial into the phone networks, and 6,200 bits per second was actually the standard speeds of modem those days that would use classical phone. Simply because that was the bandwidth supported back then by typical analog cable, right? So later on, actually, there was the invention of more advanced techniques like ADSL. However, again, this was the very first internet speeds. Okay, and then when we move on to we add noise. So again, we have to incorporate the signal-to-noise ratio that we discussed in the slides, and that of course complicates our equation, right? Because now we cannot have an infinite set of symbols because the signal-to-noise ratio limits our perception, right? So it limits our capability to distinguish between different letters, right? So from these equations, well, the ideal system would be to have like infinitely large set of symbols, and then you can go to infinitely large speed of communication or channel capacity, sorry, right? However, here we are more realistic, and we say, okay, like you cannot have microscopic changes in your voltage level and call it a new symbol, because you have you need to account for the noise, or to be specific to the signal noise ratio. And with this actually taken into account, we transformed to this Shannon-Hartrell theorem. So again, we have the bandwidth, we have a logarithm base 2, and we have 1 plus signal-to-noise ratio. Again, this is in linear scale. Most often I would refer to signal-to-noise in the decibel scale, because that's the standard, and you might need to calculate something. So here I go again, right? So we basically have the channel with 3.1 kilohertz bandwidth with signal-to-noise of 30 decibels, right? So what we're doing here, we can carry, we have, again, 3,100 kilohertz, that's our bandwidth, logarithm 2, based on 1 plus 1,000. So this 1,000 is simply transform 30 decibels, right, from signal-to-noise ratio. And now we actually increase our communication speed to 30,000 bits per second, right? So what's basically the difference between the previous case I explained? So over here, we are kind of taking, very naive approach, right? So even though we, of course, as I mentioned earlier, the M should be as large as possible, but the first technology was operating simply with ones and zeros. So our set was actually limited to, m equals 2, simply because that was back then considered, natural. I mean, the computers were operating in binary with ones and zero, so it seems reasonable to transmit the same ones and zero over the phone cable. However, what we learned here that actually we can do much more, simply if we can assess what is the noise that we expect in our cable, right? And then actually it doesn't make any sense anymore to sense only ones and zero, but we can have multiple amplitude levels for our signals. And that will be our set M, that will be the size of our alphabet. Now, how many of the sets we can do? This corresponds to our signal to noise ratio, right? So the more signal strength or the lower noise, the more distinction we can make between different symbols. Is this more or less, is this concept more or less clear? Okay, hopefully it is. Or you're not falling asleep. Okay. So now we will go back to this theorem a little bit later. But now I wanted to discuss what actually happens when we have different errors or different strategy for error correction. So basically, there are two main principles: the error detection and error correction. Okay, so by detection, we simply mean that if there are errors in the transmission, we want to be able to detect that there is something wrong. Okay, so we add redundancy, and we don't know what is the correct answer, but we know that there is something wrong. Okay, so in a way, this is when we're actually designing exams, this is more or less what we how we try to do it, right? So have an easy way of detecting whether your answer is correct or wrong. And of course, if it's correct, then you get the points. If it's wrong, we are not sure where the mistake is, but again, we know that we need to look deeper into the problem, right? And then error correction, this is added redundancy, which does not only detect, but also corrects at least certain class of errors, right? Because obviously we operate here with probability, so you're never 100% guaranteed that that you correct all the errors. There always may be some problems. However, yeah, you want to make sure that you are able to correct errors that occur with the highest probability, say. So if you can imagine which one of the two approaches is better, or what may be the trade-offs here, or some problems. Yeah. So that's the time for you to speak up. Hello? So if you think about this, two types of errors, like which one do you think is preferred? Do you want, just to detect errors, or do you want to detect and correct them?
So it seems that the error correction method is better because it's already correcting the error, but sometimes maybe we want this retransmission, which occurs in error detection method. So to be extra sure.
Yes, you're completely right. So obviously, if we can do it, the error correction is much better than just detecting errors, right? Now, but obviously there is no free lunch. So if you want to do the error correction, you need to pay some extra price for it. So what you imagine might be the consequence or the price over here? So basically, if we know that error correction is better than just error detection. The question is, what is the price that you want to pay for this extra capability?
I know that there are systems in which you can't do error correction because there is just no time. The extra latency of retransmission would be fatal. So
yes, that might be actually one argument. So the processing time. Yeah, in a way, partially yes, but this is something that is typically less of a concern, right? If you think about processing time, the simple way of making sure there is error correction is let's say transmitting the same information twice, right? And then the processing is really minimal, right? But you use up something else.
So the speed of transmission, because you need to send more data.
Right? Yes. So basically, the key word here is redundancy, right? So redundancy is the extra bit of information that you need to kind of encode into your transmitted signal, right? It doesn't come by itself. So you need to engineer that. And typically, if you want to just detect error, and also it all depends what type of error also you want to detect. Right, so the more redundancy you add, the better error correction or error detection you can have. But as you say, the price you pay is, of course, that this redundancy, this extra bit, will decrease efficiency of your system. So because you also need to transmit them, right? So in a way, if I would, let's say, repeat, every sentence twice, of course, even with high background noise, you'll be able to understand that. But obviously, the lecture would, finish up after. Well, we need double the time to do the lecture, basically, right? So basically, the more either detection or correction you want to embed into your code, the more redundancy you want to add. And of course, the trick is to add it also in a smart way. So just repeating twice is not very efficient way of doing that. We have some mathematical tools to do it very well, but we'll talk about that shortly. Okay, so for error detection, the simplest implementation, which I'm sure you are already quite aware, is simple parity control, right? So we have a bit stream, which is k-long blocks, and we add error control bits. So it actually doesn't have to be a single bit. It can be more than one or, well, 2 or 3 bits, right? So the simplest tool, of course, is single bit parity control, which just tells you whether the sequence of sent by the block is even or odd, right? So, but bear in mind actually that if you have just one bit, this doesn't really prevent you from if you have 2 bits flipped, right? Because if you have 2, 4, or 6 bits that are mistaken, your single bit parity control is nothing, right? You can throw it into a bin because you detect error. You don't detect errors that are there, right? So of course that's why I said that you can have more than one control bit. And of course, the more control bits you have, the more flipped bits you can detect, right? Because you're embedding more redundancy into your code. But of course, your block length will also be larger because you still need to send this R control bits, right? So again, as said, this is inefficient when you think about multiple errors, right? Because then if you have a lot of bits flipped, you need to add very long error codes, and then it's not that much efficient. Now, the cycling redundancy check, this is something that was, well, we won't go into details of that, but basically this is some sort of advanced technique, but it's of course used nowadays in telecommunication systems. So basically for that, the main idea here is that instead typically if you think about the classical parity control, you are just having a number and you get the reminder of division by that number, right? That's typical parity control. However, it turns out you can design a certain type of polynomial, and again, it's not any polynomial. It's basically a specifically designed type, which are designed to capture specific types of errors, right? And then it's pretty much the same principle as in the previous step, just instead of, again, dividing by a number, you divide by polynomial. Okay, and then of course the receiver compares the reminder and checks whether there are errors or not. Again, same principle applies as for the parity check. So basically for longer polynomials, you have much higher efficiency of detecting errors. But the advantage is that this is like the polynomial which is pre-agreed. So it adds, okay, division by polynomial adds of course to your computational power in that context, but in general you don't transmit the very polynomial with your data. All right, so there's this principle that to get one more that you linearly need to more bits to get linearly more error detections, right? So we can have longer polynomials with, well, there'll be still impact on the number of bits, of course, because you need to capture the reminder, but it is simply more efficient way to go. And of course, other way is you can have shorter data blocks, right? So that's things in proportion. Now, two high-level strategies basically in dealing with errors, right? Because we said how to detect them, but there is actually another question, what to do when you detect you have errors. And basically there are, so IRQ, that stands for automatic repeat request. And this is basically the request which is called upon when something is wrong when you detect errors, but you don't. So this is the time when something is wrong because you use your error detection codes, but there is no error correction really. So again, something is wrong, but you don't know what exactly. So you want to sort out things with your transmitter, so to say. And basically there are like two approaches. So first, the very simple one is that the transmitter always waits for confirmation of correct reception, and so basically it sends the package, it gets the answer, and only then sends another package. Now, another approach is simply go back and IRQ, which means that the transmitter just continuously pushes on blocks of data, and on the run, while it's doing that, it simultaneously processes the confirmation that each block was received, right? And in the case, of course, there is no confirmation within certain amount of time, it's just then they will retransmit another block. So basically, which you think, which of those is preferred here? I mean, well, you already got some answers at the bottom of the slides, right? But so okay, so typically the advantage of stop and wait IRQ. This is basically something is simplicity, right? So if you want to have a simple receiver, you would go for the first approach. However, most of the systems right now, including the TCP protocol, so the protocol that is foundation of the internet, would use go back and IRQ. Simply because it's more efficient, right? Because here, especially if you're communicating over large distances, there might be some latency or delays in your signals, and you'd simply lose quite substantial amounts of time just doing nothing and waiting for the reception. Okay. In this case, of course, again, you can do the communication much more efficiently. However, you need some sort of a mechanism to arrange the block and keep track of everything. So typically for this approach, you need more computational power. However, by modern standard, this is usually not a concern, right? And there are some embedded mechanisms also to keep track of packages, and especially if you think about the TCP protocol and the internet, when the same package can actually travel through multiple, sorry, not the same package, but the packages between two end devices can travel through different routes. So there might be actually even the situation when the package that is sent later arrives earlier to your receiver, right? So this is simply, again, much more flexible, much more efficient. Okay. And then what, in terms of the error correction, so again, if we, as we discussed, if we increase the redundancy even more, we can detect some limited number of errors. So again, right, this is this principle I mentioned earlier, that the more errors you want to correct, the more redundancy you need. And this does not involve for transmission. So, a kind of classical example would be here codes which are used for CD or DVD discs, because once you buy a DVD, a disc, right, and it's scratched or there's some errors, you cannot really retransmit mistaken data, right? Because you can't go to the shop and ask for a second one. So that's why in those applications, actually, you have a physical device here, right? So over here, the redundancy is not a concern. So you can allow a little bit for including some more information redundancy, at the cost of correcting some of the errors, simply because the application does not allow you for easy retransmission. So, any questions towards the error correction or strategies? All right. Right. So we move on to the information theoretical part, and basically it may seem at first more suitable for philosophy classes than telecommunication or engineering, right? So basically we ask ourselves question, what is information? And more importantly, how we can measure information. And as abstract as it seems, we can actually do that, right? So we can put a certain number on the content of real information into our message. So here there are like three different information examples, right? So basically, what is important actually here is that we are treating information as a sort of abstract, abstract concepts, but regardless of the decision that we'll make, or any monetary value or any implication on our future lives, right? So from our point of view, the Pantadeusz book, the hieroglyphs, and some writing on the wall, it doesn't really matter. So we try to treat this regardless of the consequences each information may have, right? So for example, information about, under certain conditions, of course, information, a tip about, investment on the stock exchange that will lead to the increase of some actions, and information about, who your friend was dating last evening, they are treated the same. So it's only about the information, regardless of what this may have in, what this information may mean in the real life and how it can be interpreted. Okay, so basically there are some literature here. So those, of course, are some standard books that you saw already in the previous literature. However, the lowest one by Claude Shannon, The Mathematical Theory of Communication. This is actually quite old, but this is actually the original book which did introduce, the concept of information and how to measure information. And this was basically done by Claude Shannon, who is the father of information theory. So yeah, so this is the topic we'll cover in this lecture. So firstly, what is information, how we can measure information, and then see what are the implications of that for analog and digital signal processing. Okay, so basically this guy here in the right corner, that's exactly Claude Shannon himself. He was quite a smart guy working in the first half of the 20th century. And he was working for the Bell Labs company. So, problem back then, there was a rapid need of more efficient telecommunication systems. Also the telephone networks back at the time were getting more popular and covering vast networks. And Bell Labs was basically a company which was research-based branch of the Bell Telephone Company. So basically, company which was introducing telephone networks. And the idea was actually how to ensure that center quality of the phone call is maintained, right? Because you can imagine back then there was a lot of noises, scratches, problems. So it was just a fraction of the quality that we enjoy nowadays with our mobile phones. So basically, the idea was to try to come with systematic approach on how to measure information. And for starters, the first assumption is that we have a symbol chosen from a discrete alphabet. So basically, our alphabet can be, pretty much anything, right? So it can be either symbols that we discussed for modulation, it can be 0, 1s, binary, it can be letters of the alphabet, it can be amino bases in the DNA chain in cells. We don't care, right? It can be anything. And this is basically discrete. Now, what we have to understand is that most of the information here is discrete memory source. Okay, so basically well, discrete should be, of course, obvious because we have a discrete set of different letters of the alphabet, right? So A, B, C, and you cannot have like 3/4 of A and 1/4 of B, right? So it's discrete. The memoryless, this is quite tricky in a way, but it's just like an assumption that makes our life easier. So memoryless simply means that the symbol generated at the given time is not depending neither on the previous or well, on the next. That's even more time machine, but on the previous time. So this basically means that we can describe each symbol by a certain probability that that is assigned to the symbol. And this is basically in contrast to the source with memory, where the symbol generated as a next depends on symbol generated previously. Okay, so just a sort of example, if you think about human speech or human writing, even so, which type of those sources do you think we use as when you write? Okay, so the alphabet is clearly a discrete one. There's no doubt about it, right? But do you think that the alphabet is a memoryless or it has some memory? Okay. Let's maybe do some polling here. So if you can type your answer into the chat, what do you think? Is it memoryless or is there some memory in writing in the alphabet? So I'm still waiting for your answers here. Yes, carry on. We'll wait a little bit more for more opinions on this. Yeah. Only 2 opinions. Nobody else. So yeah, obviously, okay, both of you are correct, right? So of course, our alphabet has a memory. However, this is not necessarily because of the alphabetic order, as Jakub suggested here. It's got more to do with the natural way how we speak, right? So for starters, we have in the alphabet vowels and consonants, right? And in English, there are some exceptions. In Polish, you know that very rarely you will have 2 vowels next to each other, right? We also know that there's this concept of syllables, which got to do with the way how we produce sound, the way we speak, right? So again, it's very unlikely to have more than 3, 4 consonants next to each other, just because of the structure of the language, and even including Polish sounds like sh, ch, j, which typically consist of 2 consonants, but it's simply impossible to have unfinished, infinitely long set of of consonants. Okay. Similarly, in English, the same rule applies. The most kind of visible issue is that if you think in English language about the letter Q, there is practically no word where Q appears without U after it, right? So that's again. So basically, if you have if your previous symbol out of the alphabet was Q, you have 90 something, probably 97, 98% chances that the next letter is U, right? So in a way, you can actually think about it as U being the as Q after Q being high redundancy or just some useless letter, right? So so obviously in the alphabet, I mean in the human alphabet or writing alphabet, that we have some memory source, but this is not because of the order of letters A, B, C, D, right? This is because certain letters are more likely to occur after some letters than the other. And again, the example with vowels and consonants should be a good illustration. Okay. So, however, and in this lecture, this is just introduction to telecommunication, and we will deal mainly with discrete memoryless source. It's just, as you can imagine, that simplifies a lot your analysis, because each symbol is assigned a single probability of occurrence, so that simplifies a lot. And later on, I'll be kind of treating, well, I have a few examples using alphabet, and I'll be treating that alphabet as a discrete memoryless source. Again, it's just to illustrate some concept, right? But you should, of course, bear in mind that this is certain oversimplification, and in general case, this is that the alphabet has a memory. Okay. So so as we mentioned earlier, right, that the memoryless source means that the symbol Sn does not depend on any previous output, right? So basically, we are producing just random, well, actually quasi-random, because we want to transmit some information, random set of symbols, and the probability of occurrence at the time t is just given by the probability. Of course, this is a stochastic system, so probabilities need to add up to 1. I hope that's obvious right now. So it's like there has to be some letter, right? That is chosen from the closed set. Okay. And the last point is that each occurrence has, in a way, carries some uncertainty, which is actually the inverse proportional to the probability, right? So again, this is some reasonably natural concept for probability. So basically, the lower probability of occurrence, right, the more surprising it is when you saw that symbol, right? So what example I can use here? Well, hopefully this is anyway clear here, right? So if it's like winning in the lotto, for example. I mean, the probability of occurrence of that is extremely low, right? But there are some guys who get to win the main prize in lotto, and then you can imagine they're like really surprised. So inverse. Now the main idea, and that was like this breaking idea of Shannon, and before that was pioneered also by Nyquist, is this link of the amount of information with probability. Okay, and this is basically based on a very simple concept that, again, the less likely symbols contain more information. Okay, so basically, if something is obvious, right? I mean, I know today is Tuesday. There's pretty much no point of saying that, you know. So the information that is being transmitted is very small, right? So you want really to transmit something that is new, something that is uncertain, and then the content of information of that increases. So intuitively, I use the two sentences as an example. So if you think about the final test, you have these two sentences, right? We're talking here, of course, about the test from this model, fundamentals of telecommunication, right? And if I tell to you, and then of course, assuming that the final test will contain a question about QAM modulation, okay? What is the, without me saying that, what is the probability of that this is true? Right? I mean, pretty much 1, because we spend quite a lot of time on QAM modulation. So, you know, you are guaranteed there will be some question referring to this, right? However, if I tell you that the final test will contain a question on the Battle of Wrocławice, which is like some event from Polish history, right? I mean, you may be, what does it got to do with telecommunication? That simply, you know, that's something totally unexpected, right? So basically, you know, those two, so this would have like probability of occurrence normally closer to 1. So me telling you that, you know, doesn't really carry any information, right? On the contrary, this normally would have probability of occurrence close to 0, right? Simply because, you know, it's not the topic we're covering here. So then again, if I tell you 2 days before the test that this is the case, that there will be a question about, you know, the leaders or the outcome of Battle of Wrocławice, because the probability is very low, then everybody probably would, well, most of you would just go to the book, study what the hell is Battle of Wrocławice, right, and remind some facts out of that battle, right? So the content of information in that case would be much higher, simply because you were not expecting that to happen. This is, I hope this is clear, more or less. So this is just some sort of analogy to get some, you know, intuitive grasp on this link between probability and amount of information. Is this clear so far, or are there any questions? Okay. So I think we can move on. And just for the record, of course, there will be no question about Battle of Wrocławice at the final test. This is just an example. Okay, so with that, we move on to some qualitative measure and the concept of entropy introduced by Claude Shannon in the context of information theory, right? So you might be actually quite familiar with the entropy used typically in physics, which is the, you know, metric from thermodynamics, basically, which is the metric of how much a given system is chaotic, right? So in a way, this was at the time very, very controversial of using the term entropy. So we are talking here about different entropy than in the case of thermodynamics. However, some parallel should be quite obvious here, because the entropy tells you within given alphabet how much surprising it can get, to say the least, or how much information is on average carried by symbol in an alphabet. Okay, so basically the higher entropy, the more the less certain you can be about the outcome, but also the more information you have, right? So basically there are these three application here. So firstly, the entropy is the average information symbol in alphabet. Okay, this means if we are producing infinite set of symbols, we've given each symbol assigned this probability in a memoryless system. If you take this average from minus to plus infinity, you would get basically that each symbol carries amount of bit as dictated by the entropy, right? Secondly, because of the link that we said earlier of that information is linked to the probability, and this average information also corresponds to the uncertainty of a symbol's occurrence. Okay, so basically, how certain you can be. For example, if you have a two-symbol alphabet with ones and zeros, but one symbol has probability of 1, the other obviously need to have probability of occurrence 0. There is no surprising here. I mean, you will get the infinite set of the same symbol with probability 0, right? And then the more and then if you think about probability 50-50, then you cannot really predict reliably what will be the next symbol, and that's what measured with entropy. Okay, and then this actually linked to the first one. So basically, entropy is also used to calculate the average length of a code word when optimum coding is used. Okay, now what does it really mean in practice? This statement is actually linked with the first one. So as a principle, you know that the entropy allows you to calculate average information per symbol in alphabet. Okay, so if your coding is optimum, it means actually that it is as close as possible to the real average information content per symbol. Okay, because if you got more information, then that's the redundancy. That's where you're not really efficient. You're transmitting more than you're supposed to. Okay, now if the average length of code word is actually less than the optimum coding, that means you're missing something. That means information loss and uncertainties, and that can cause problems. Okay, so basically, we'll look more into some examples later on. For the time being, just wanted to point out that the third is actually linked to the first one, right? So with the optimum coding, you simply try to be as close as possible to the real average amount of information. And how it is calculated. So basically, the entropy is, of a memoryless system can be calculated as the sum over all alphabet of the probability of occurrence pk, where k corresponds to the given symbol, multiplied by logarithm base 2 out of inverse of this probability 1 over pk. Okay, bear in mind that this is over here we have like inverse of the probability, but of course this is a logarithm here, right? So equivalent, you can simply use the pk and put a minus sign in front of this equation. Shouldn't really matter. So with that, let's see on the classical Bernoulli process. So we're flipping a coin, right? And the coin can have either heads or tails, or 0 or 1s. And we are assuming here actually this is not a normal coin. So the coin is kind of tricked to have certain probability of 1s and 0s. So so for a fair coin, when the probability of having 0s or 1 50-50, we can calculate the entropy simply as half multiplied by logarithm 2 from from 2, which is 1. We add 2 halves and we get the entropy 1. Okay, and that pretty much is the most uncertain case, right? So this intuitively should be the highest level of entropy that we can get, because it's 50-50. You never really know what will happen. Okay, then if we try to change the probabilities, right? So here we put the pk, so the probability of 0, as 0.25, right? And this means, of course, that the 1 has probability of 0.75. And we do the same thing, right? So we calculate entropy. So 1 over 4 multiplied by 2 because it's logarithm base 2 out of 4, plus 3/4 multiplied by 0.46. So this 0.46, this is, of course, logarithm base 2 of 4/3. And we get actually the results 0.94. So what this number actually tells us? It tells us really that for anything different than 50-50 probability, we will have less entropy, right? So the system will be less surprising in a way. Of course, up to the point when we'll have probability of either 1 or 0. And if we would calculate, pk from ranging from 0 to 1, this is the entropy that will get calculated. Okay, so again here, this is entropy equals 1 for the pk when we have like this 50-50, so the fair coin toss. And that's the least predictable system. Okay, and then when we go towards probability 0 or 1, it doesn't really matter which way we go. We actually decrease our entropy. We make the system more predictable, right? Up to the point that when we have the probability 0 or 1, well, in that case, we know we'll always get 1 or always get 0. So there is no point on on bothering actually with stochastic system anymore, right? And in that case, our entropy will be 0, because there's no possibility in the system that we get anyhow surprise. We just know it will be either infinite row of zeros or infinite row of ones. Okay. Now, so this is of course the probabilistic description, but here we're speaking with the information theory, and that's the also interesting aspect that this entropy is basically linked to the information content. Okay, so if you think about the 50-50 split, so the third time cost, that actually means that that actually means that there is one bit of information once we know the result of the toss. Okay, so typically, there's one bit because we have a two-letter alphabet. It can be either 0 or 1, head or tails. And once we learn about that result, of course, it will be one bit of information. However, this is actually not the case if we change with the probability pk, right? So for example, from the information theory, if we have 1, 2, 3, 4, so if we are here, right? So we have the probability pk 0.1, and the probability of 1 will be 90% really, right? So basically 90% of times when we're here at this point, 90% of times we will get 1 as our coin toss. Okay, So how much information actually would the results of a single coin toss contain for such a system? Any guesses? Right. So you have the probability of 0 being 10% and probability of ones being 90%. Right. So this is this point in our curve. And then if you learn about the results of a single coin toss, again, how much information will that have? Okay, so again, let's go to the chat, and who thinks it will be 1 bit? Okay, so let's do it this way. I will write in chat different replies to this question, and you can like the answer you believe is the correct one. So 0 bits, 1 bit, and other. Let's make it this way. So if you can click like next to the option you believe is the correct. Okay, and well, I saw one reply next to other, which was removed, and most of you think that the correct answer is 1 bit, which is not exactly the case, really, right? So again, looking back at this curve over here, right? The content of information would be 1 bit only if you don't know what's going on. If both ones and 0 or head or tails have the same probability, so you cannot make any reasonable predictions about the system, right?
So this is this case where you told us that this less probably case has more information. Yes.
Yes, the less probable case has more information, but once it occurs, right? But on average, so statistically, of course, it's got less probability of occurrence, because that's how probability is defined. So overall, okay, so sorry, I should maybe clarify this. So overall here, we are speaking not about single symbol, and that's actually quite important distinction here, okay? We are not interested in the single symbol, we are interested in the full system, right? So again, we have this system which is generating heads and tails, one with 10% probability, the other with 90% probability, okay? And actually it turns out that one symbol generated this way will have entropy, will have information content of 0.5 of half of a bit. Okay, and this number comes directly from the calculation of entropy. So you can put here, the probability of one symbol being 1/10 logarithm to base 10 plus 9/10 logarithm base 2 10/9, and this is basically the number more or less that you should come up with, right? So On average, yes. If you get the symbol that is less probable, that's more informative. However, on average, you're like not very likely to get that symbol overall, right? So at the end, if you do a betting in this bet, your payoff would be higher. However, it's not very wise to bet for the highest payoff, not at least without some additional information, right? And overall, the predictability of the system will be higher, and the entropy here will be 0.5, which means the average amount of information in a single toss is only half of a bit. Is that clear to everybody? Right. So again, what we're trying to make a distinction here is with the entropy, you don't look at the single symbol. You look, at the full system that you're looking at. Okay. Sorry. I know is that. I hope this concept is quite clear, or possibly you need some more time to think about it. Okay. I mean, in any case, why this is important? Okay, this is important because it goes back to the to this idea, of efficient transmission, right? So you want to transmit only the amount of information that is really there, right? So in this case, actually, you well, if you have a discrete set of letters, you cannot transmit, let's say, half of a bit of information for the system. However, in many cases, you can use this framework to your advantage. Okay, so basically thinking about that, this is the example I mentioned earlier with the Polish alphabet. Okay, and over here, this is we are trying to calculate entropy for Polish alphabet. And of course, the most naive case is that, we have a random set of letters with each letter occurring with the same probability, right? So again, we have a probability of occurrence of a letter 1/32 multiplied by logarithm base 2 out of 1 divided by pk, which basically should give us 5 bits per symbol. Okay, assuming again this naive approach of assuming each letter is equiprobable. So this is our highest peak on the entropy curve, right? We don't know anything about our systems, and well, we know here that you can pretty much transmit. I believe. In that calculation, the space is not included probably, but in any case, you can transmit, any Polish words using only 5 bits, right? Assuming a bit is a binary thing, 0 or 1. So with 5 bits, you can transmit any symbol, assuming uniform probability distribution. However, sorry. Oh, I don't have this. Okay. However, in real probability distribution is much different from the uniform, right? So you know that, well, in Polish alphabet, A is definitely the most popular letter, which is with the probability of occurrence over here. I think E would be either second one or pretty much at the top with 0.71. Well, in general, vowels have a higher probability of occurrence than the consonants, right? And well, basically, if you played Scrabble, this is exactly the reasoning behind the points, right? That each letter of the alphabet has different probability of occurrence. Bear in mind that we are still here assuming this memory-less source, right? So that each letter is described by the own probability. And if you take these probabilities into account, you would actually realize that and calculate entropy. Again, same equation, just putting real probabilities rather than the uniform probabilities. You will actually realize that the Polish alphabet is somewhere around 3.2, 3.4 bits per symbol. Okay, so at the end of the day, okay, you cannot maybe have 3.2 bits per symbol, but if you allocate, 4 bits, you can actually you can basically use much more efficient system because you're saving 1 bit out of 5. That is just redundancy. If you take to the account the real probabilities. Is this concept clear? So I'm.
So
I
in
think
general,
so.
Okay, go on. Yeah, please. In general.
So in general, we have that if the probability isn't uniform, then the number of bits per symbol is less than in the case where it would be equal. Yes.
Yes, indeed. This is exactly the message here, right? So we can be more efficient with transmitting information, right? So typically the uniform probability, that's when the entropy is the highest, right? Because again, you are never certain which symbol comes. I mean, every symbol is equally probable. When you put your real numbers, real probabilities that are not uniform, this is something which gives you some insight and predictability of the system. It's not Lotto anymore, right? It's got some structure, and then you can decrease the amount of information to be closer to the real information content. Okay, now so far this is only of course a theoretical approach or half of the story, because the entropy tells us that we can do better, we can do more efficient, right? But it doesn't tell us yet how to do it. But we'll move on that in the next hour probably or so. Okay, but yes, this is basically the message, that the uniform probability is typically the worst case scenario from the system, because you can. Okay. So yeah, somebody has something.
Yes. For example, if we have a file, like we have a file on the drive, and it has some entropy. If we would to compress it, we effectively increase the entropy.
Not really, because so it's the other way around actually, right? So when you do so you see the entropy it's there, right? That's the theoretical limit of the amount of information on the file, right? When you do the compression, you are removing redundancy or removing the bits that are not that much relevant to the system, so to speak, right? So right? So for example, if let's assume this is I mean, let's assume you have in your data, you will have a certain sequence. So 5 bits going, let's say, I don't know, like 11101, right? That's 5 bits which will occur very often in your uncompressed file because of some structure of the data, right? It might be some header, it might be I don't know, well, in a text file, let's say a new line, that's something that will occur very, very often, right? And that takes up, let's say, 5 bits in your raw file. But because it occurs very often, you can create a code where those 5 bits are, let's say, allocated to a single bit, right? Then, of course, you have to realign all your other symbols to make sure that the new symbol does not collide with already existing symbol. But pretty much that's exactly how compression works, right? So it allows you to preserve the same information content, right, while using less space on your drive. So less, less bits interpreted as 0s and 1 on your drive. So this is actually one aspect of the naming here that can be confusing, right? Because in information theory, when we speak bit, we typically mean some, the amount of information. And this is related to the bits that we see in computer systems, which are usually considered to be 1s and 0s. But it's pretty much not the same concept, right? So so typically the entropy would be the same for both files, right? However, the amount of space on your hard drive of the compressed file is simply closer to the theoretical limit than the raw file. And that's basically the idea of compression and how it works. Okay? Does that make sense?
Yes. Okay.
Okay. Great. We'll also see some examples of that when we move on to the what's called the Huffman code. And again, just excuse me. So basically, we already spoke a bit about the redundancy. So exactly this redundancy is the presence of additional information, right, that is repeated from the information theoretical point of view. Okay, so typically, the most intuitive case I was using so far is that you simply, repeat the same thing twice, right? However, here this is done in the more in the information content, theoretical content, and the probability, right? So yes, if you repeat the same thing twice, you have a redundancy, but also another form of redundancy might be, if you have a symbol with low probability of occurrence, that is allocated multiple symbols or multiple bits, right? So the example here, for example, the Q and U system, right? So typically, any additional bits over the theoretical limit given for the system by the entropy, this is redundancy. Okay, and this is the something that can be seen as a wasted spaces if you're doing, compression with a zip of your file, but also in the context of telecommunication, of information, it allows for some error either correction or detections. Okay, and this is the topic that you mentioned earlier, right? Also, in the context of compression, it again still uses this information theoretical concepts, but pretty much we can have two types of compression. Okay, so basically we have the lossless compression, which basically means that you do the compression, and after the compression you get exactly the same information as before. So there's no loss of information in the process. And this is exactly the case when your compressed files aims to reach this theoretical limit of informations per symbol given by the entropy, but not less. Okay, so you try to approach this limit, but not exceed it. And this is, for use for text programs. Well, most of the zip and there are protocols use exactly this form of compression. However, we do have lossy compression as well. Okay, so actually in this lossy compression, we lose some information, And that basically means that the average symbol, average amount of bit per symbol in the coding can be hypothetically below the level of entropy, which means we lose part of the information, so we cannot recover the original copy. However, there are applications which we say we don't care about that. We can afford losing some information here that doesn't really matter. Okay, now, can anybody tell me some examples or even application where such a lossy compression actually does make sense? Okay, so basically, obviously, when we have any sort of database, any sort of program, we cannot afford losing information, right? Because that information might cause our program to malfunction, right? Or our data to be skewed. However, where actually we can afford losing tiny bits of information.
Can you say the question once again? I didn't hear it completely.
Sure, sorry. So basically, what is the type of application, or even if you can figure out type of a protocol, a file type, when it makes sense to apply lossy compression? So what might be the context, just from the top of your head, when we don't need to exactly recover all of the information, just a sufficient part is good enough?
For example, music and video, because it has some redundancy in our minds.
Yes, indeed. I wouldn't use the word redundancy here, because redundancy typically applies to the information that is repeated, right? So when you remove redundancy, you don't really lose information as such. You remove more than just the redundancy. But yes, that is exactly a very good answer, right? So music, video, images, this is exactly where the lossy compression is applied, right? So thinking, for example, in the JPEG format, where you typically remove the high frequency components of your image, right? So the high frequency in that context, we mean pixels that that change rapidly over an image. And as you said, like it allows good benefits, whereas the resolution of our eye or our ear in most cases is not doesn't really see the difference, right? So MP3 format, that's another example of lossy compression. Okay, so yeah. Again, bear in mind this is controlled, right? So you lose just a small fraction of information that you consider is still okay to get the impression about the image. Okay. Now we are 1:45, so I would suggest we stop here for the moment and we make like a 15 minutes break up to 1 o'clock, and then we'll resume with basically some concept of digital and analog signals and putting what we've learned into some more practical content. Okay. And are there so far any other questions? Okay. Okay. So again, let's meet back in 15 minutes from now, and thank you so far.